Hello and welcome to another Lorium Technology workshop. Today's workshop is on the OpenEvo methodology. I'm your host, Steve Phillips. I'm the lead designer for the FPGA Logic, and I'll be walking you through our methodology today. Today on our workshop, we'll be looking at the prerequisites you'll need to have before you start. We're going to look at the building blocks of our OpenEvo methodology, including the libraries EvoBSP and EvoBuild template. Then we're going to look at the FPGA architecture and the board support package that it includes and see how we integrate new custom logic into that. And finally, we're going to walk through an example design we call the Evo PMUX CSR to see how we integrate custom logic into the Evo FPGA. So, prerequisites. First, we're going to assume that you've already completed our OpenEvo Quickstart workshop. That's the video that you should have watched before this one that walks you through the process of installing the Arduino IDE, the Intel Quartus tools, and running through a compilation process of the OpenEvo design, the base design, and getting it written to your FPGA. So that gives you a base functionality that we can work from. We're also going to assume that you're familiar with Verilog, that's an HDL, or hardware descriptive language, and FPGA design. What we mean is that we're not going to teach you how to write Verilog or how to use FPGA design tools, but we're going to assume that you have some familiarity with them so that we don't lose you as we're explaining things. The tools we're going to need installed are the Arduino IDE and the Intel Quartus Lite edition. This is Intel's free as in beer, version of Quartus. And actually, you should already have these installed if you've gone through the Quick Start. We're going to need the OpenEvo libraries installed, the EvoBSP, and the EvoBuild template. And again, if you've gone through the Quick Start, those should already be installed. In addition to those two, you may want to install the Evo PMUX CSR. That is the XP library for the example design we'll be going through today. And finally, you're going to need an Evo M51 board and a USB cable to connect it to your computer. So now let's dig into the two libraries, EvoBSP and EvoBuild template, to see what's in them. Now, when you're working with the Arduino GUI, you're required to adhere to their Arduino IDE library specification. We've got a link to that shown here. And what that means is that you got to have a set of directories underneath the top of your library that are a certain structure in order for the GUI to know where to find things. Now, what we are going to do is use the extras library, which is kind of a catch-all extra directory within the structure where you can put anything you like. And what we like to put in there is our OpenEvo stuff. Now let's take a look at what's in our EvoBuild template extras directory. There's a design directory that holds 3 files. The first is the EvoXP, and this is the top level file for all the custom logic in our design. The EvoXP info file is how we add custom info CSRs for the custom logic. And the EvoXP address package is where we specify addresses for any CSRs that are embedded in the custom logic. In our Quartus directory is a familiar set of files. As we saw in our Quick Start, these are under control for the most part of the OpenEvo update script, with the exception of the OpenEvo.qsf file, which we'll be using to specify files that we're adding to the design. In the EvoBSP, we have files needed for compilation in the Quartus directory. The evocommon.qsf is our master QSF file, and it controls the compilation process. The evocommon_pins is the pin assignments for the design, and the Evo M51 SDC are the timing constraints for our design. Then we have 2 sets of 3 files, one for the M25 size FPGA and one for the M50 size. The first is a .sof file, which is what we call our factory image. In the Max 10, the flash can actually hold 2 images. So what we do in OpenEvo is we use image 0 for what we call our factory image, and image 1 is for custom images or OpenEvo images. In order to boot into the factory image, you ground a certain via on your board while you're turning it on. And this is kind of a safety feature. If you design a custom OpenEvo image and burn it to your FPGA, and now the FPGA is wedged and you can't get it to do anything, you can't even get it to accept a new image that you're trying to write to it, then what you can do is reboot your board, grounding that pin, and you'll come up in your factory image, and then you'll be able to load another image if you like. So it's kind of a safety feature. It allows you to go back to a known good image just by grounding a certain pin on your OpenEvo board. The next file we have is a QXP file, which is an IP block. In this case, it's the IP block that contains all the board support package design. And there's an evoinfo.qsf. It corresponds to that has settings that match that particular BSP. The other set of files that are in our Quartus directory are the master copies for our OpenEvo update. So these are files that will copy into UXB when you run the update script. In the design directory, there's a number of source files and an IP directory with IP blocks in it. These are all the files that you need in addition to the BSP IP block in order to build the design. And finally, we have our tools directory. There you'll find your OpenEvo update script, your Evo flash load program, and the Evo convert image tickler script, which takes that SOF that comes out of the compilation process and converts it into the Evo image format that we need for the Evo flash load program. So here's the methodology that we use in 10 steps. First thing we're going to do when we're creating a new XP is we're going to copy the Evo build template into another folder and name that folder whatever it is that you want to call your XP. And then we're going to take all your custom logic that you want to have and copy that into the extras design directory of your new library. Then what we're going to do is modify our EvoXP wrapper, instantiate your custom logic into it, and connect it up to the other parts of logic that are in there. Then we want to modify our address package file so that we can enter in the addresses of the various CSRs that we've added in the custom logic. And finally, we're going to modify our EvoXP info file to add any additional info CSRs that we want to add. In the Quartus directory, we're going to modify the OpenEvo QSF file and specify in there any additional files that Quartus needs to know about. Now that we've done all of our modifications, we can go in the Quartus directory, double-click on that evo.qpf file, and that'll load up Quartus and then load that project file. Since this is the first time we've run with this XP, we're going to run our OpenEvo update script, which will make sure that our XP is compatible with our Evo BSP. And then we're going to compile the design. Now, normally the first time you try to compile, you're going to run into errors. Maybe you've got syntax errors, maybe you've got typos, maybe there's just something about the way you connected it up that Quartus doesn't like. You'll have to take a look at those errors, go back, make changes to your source code, compile again, keep going in that iterative loop until you get a clean compile. Once you have a clean compile, then we can run our Evo flash load, which will move that new image into your FPGA, and then you can go and run your hardware. So let's take a look at the Evo FPGA architecture and the logic that's in the BSP and how we can add custom logic into that framework. Here we see a very high-level block diagram of the FPGA and the board and SAMD that are connected to it. As you can see, there's a white area on top. This is the unused fabric that we can add custom logic into. And this gray area on the bottom is the BSP logic. Now, I know it looks like the BSP is using up most of the FPGA, but in reality, the BSP uses about 1/3 of the FPGA when you have an M25. For an M50, it's 1/6 of the area, so there's plenty of room left on these FPGAs to add custom logic. The pins on the FPGA are arranged into ports, much like you'll find on the SAMD, and in fact, we tried to emulate that as much as possible. On the right side here, we have a D port, an E port, and a G port. These ports are directly connected to the vias and castellated vias of the board. On the left side, we have the F port and the Z port, or Z bus. These ports are directly connected to the SAMD and allow for communication between the FPGA and the SAMD. We also include what we call our D2F module, which is a pass-through module that connects the F pins to the D pins such that we can control the D pins from the SAMD in a pass-through fashion. And in fact, there are no sequential elements in that path. It's purely combinatorial. So when you toggle pins on the SAMD, it appears as if those D pins or vias are directly connected to the SAMD. Also connected to the SAMD is our I2C block. This is for our CSR, or control status registers. And this is the master now on the CSR fabric, which is then connected to all the other blocks in the design so that the SAMD or the user can read and write the CSR registers through this I2C. And finally, we have our flash load control block. This is a wrapper around the FPGA flash. And this allows us then to write data through the SAMD, through the I2C, into the flash load, which then writes it into the flash, such that you can load new images into your FPGA without using a JTAG connection. You just use your normal USB connection to the board, and there's the EVO flash load program uses a program running on the SAMD to transfer data for you. Let's take a little different look at the architecture. This is more kind of the hierarchical view that I prefer. This is kind of a box at the top level of the chip, and we can see at the top level we've got several blocks instantiated. The Evo BSP, which we saw in the previous slide in a lot different format, the EvoXP, which is our wrapper around custom logic, and there's an Evo clock reset block, which is a wrapper around the PLL, and it generates all the clocks and resets that we need in the design. In the Evo BSP, we can see we still have our I2C block and our EVO flash block. This is the wrapper around the flash. And then we have this one called the Evo GPIO, which has got 5 instantiations of the port logic, one for each of port D, E, F, G, and Z. So just a little bit different way to draw the BSP. And in this case, we're kind of putting it in a hierarchical view, that the way the logic is actually designed. In the EvoXP, which is our wrapper around custom logic, there are 2 blocks that we always include. The first is the EvoXP PMUX, which allows access to the pins in the ports. And the other is the EvoXP info block, which provides info CSRs for the custom logic. The other blocks we see here, these white boxes, those are an example of some custom logic that somebody might design and instantiate into the EvoXP. So you can see that these other custom blocks are instantiated at the same level as the PMUX and the info blocks here. The I2C block over in the BSP is the master for the CSR Avalon bus, which you can see is connected to the other blocks in the BSP and also has a connection across into the EvoXP. And we've got the XP info block connected to that CSR bus, but also there's a couple of user blocks that are connected. You can connect to the bus or not connect to the bus. It's up to you, depending on how you're doing your logic. But it's easy just to add a slave port on that bus to connect any block you have up to that CSR Avalon bus. We can see that some of these other user blocks are connected to each other. There's really no limit on how you can interconnect things within the XP. So you might have some IP blocks and some custom logic, and they're all interconnected in some way that maybe only has a CSR connection back to the I2C. You can also see that some of these blocks have connections to the PMUX, and that's how they'll be able to control pins over here in the port logic. Let's take a closer look at that PMUX logic. Inside of the PMUX block, there's actually 5 PMUXs in there, one for each port, D, E, F, G, and Z. Each one of these PMUXs is the same width as the port. For instance, port D is 26 pins wide, so our buses are 25 to 0. Coming out of the right side of these are what I call the triplet buses, the dir, out, and enable buses, each of which is the same width. The way this works with these signals that are going directly to the ports is that if a bit in the enable bus is set, then the corresponding pin in that port will be controlled by the corresponding bits in the dir and out buses. So for instance, if bit 3 of the enable bus is set, then bit 3 of the dir bus will determine whether that pin is going to be an input or output. And if it's an output, then bit 3 of the out bus will determine the value of the pin. On the left side, we again have our triplet buses, dir, out, and enable. And these are fed through the MUX to the right side. The number of inputs here is controlled by what I'm calling below here the MX number, equals the number of control inputs per pin. And this is an integer from 1 to, say, 10 or so. I don't think there's really a hard limit on that number. But what that does is if that M number, in this case MD for port D, is a 1, then we have a simple parity between the two sides, left and right. They'd both be 26 bits wide. If M is a 2, then the right side here, these are going to be 52 bits wide. So in effect, you'll have 2 inputs for each pin. And then in the PMUX, there'll be a select MUX for that. So let's take a look at that. Here we see on a per bit basis in the PMUX, there's a select for the dir, there's a select for the out, and then we have enables coming in down below. So if that M number of inputs is a 1, then these MUXs essentially have a single input and they're just a pass-through. If M is a 2, then there would be 2 inputs to each of these MUXs, and the enables there'd be 2 enables coming in and they would select which one of those was active. What you want to be careful here is that this logic assumes that only one of those enables is active at a time, a 1 hot. So you'll want to make sure in your control logic that before you're going to change who's controlling a pin, you want to turn off all the enables first and then turn on the one that you need. So that kind of explains the architecture. Now we'll go through our PMUX CSR and see how we integrate into that EvoXP module. So what we're going to do is, since this is a new XP, we're going to copy the Evo build template and call it Evo PMUX CSR. Then we're going to copy our new source files into the design directory, and then we're going to modify that top level file, the EvoXP, to instantiate our new design. Now in this case, we have a already completed XB, so we can see after we've already done these things what we'll end up with. We have an Evo PMUX CSR directory with an extras directory in it, and then inside of that there's a design directory. You can see we have our same 3 files here that we had in the build template, but we have one additional file. This is our custom logic that we're adding. And in our Quartus directory, we have all the same files that we saw in the build template. Again, these are all under control of the update script except for OpenEvo.qsf. So let's first take a look at our new custom logic. It's the Evo PMUX CSR module. And this is a module that we developed during testing of the PMUX. It allows us to essentially hang a whole bunch of CSR registers on the inputs to that PMUX, and then we can verify that we can control those and then control the pins through the PMUX. So this logic gets a little bit more complicated than we really want to get into today. So what we're going to do is we're just going to take a look at the I/O signals of this module, and then when we look at the EvoXP, we can see how we're instantiating that and connecting it up. So let's take a look at that source file. So here we see our Evo PMUX CSR, and we're going to scroll down a little. Here we can see that we're setting some parameters up that have addresses for various CSRs that are in this design. And we're setting them to 0 right now. We'll assign the values once we get up one level. And here we see the input-output logic. We have our clock and reset as normal. And here's our PMUX buses. The dir out and enable buses are outputs going to the PMUX logic. And then we have the PMUX in bus that's coming directly from the port without going through PMUX. These signals here comprise our Avalon CSR slave interface, and this is how the I2C module can communicate with our custom logic. So let's go back to our presentation, and now we're going to go and take a look at the EvoXP. This is a wrapper around all the custom logic, and it provides a standard set of I/O into this wrapper that provides all the clocks, the resets, the PLL control signals, all the buses coming from the BSP that you might need for your custom logic. It also instantiates the EvoXP PMUX and the EvoXP info blocks as standard, and then allows you to instantiate any additional blocks that you might want to add. We'll skip past the comments. And here we can see our I/O. We have clock reset, of course. Then we've got all these clock and reset and enable signals and PLL signals. These are coming from that clock reset block that's at the top level. So you have access inside of the EvoXP to all the clocks, resets, enable signals that we can provide. Next, we see 5 groups of PMUX signals. These are the dir out and enables coming from the PMUX going out to the ports over in the BSP. Or in the case of the PMUX in, their signals coming back from the ports. And then we've got our standard Avalon slave interface. Here we see the EvoXP info block is being instantiated with its slave interface. And then we've got our XP PMUX module. First thing you see here is we have some local parameters, one for each port, and this defines the width, or that M value that we talked about earlier. That parameter then is used as a multiplier into the width of these buses that we're defining as input buses into the PMUX logic, 3 of them, one for each of the different PMUX blocks. Then we can see the instantiation itself, where we're passing those width parameters, those M values, into the instantiation as input parameters. And then we are connecting up our buses that are coming from the PMUX CSRs that we'll see in a minute, input signals or input buses into that PMUX. And then we've got our output buses going out to the ports to control those pins. And at this point, we can instantiate our own custom modules below here. So here we see the first of the PMUX CSR modules being instantiated. We pass in that width, that M number. We pass in the addresses here that match up with these addresses. These addresses here will be defined in our address pack. As I/O, we can see we're connecting up our PMUX buses. This this triplet of dir out enables are going to our PMUX block, and here we have the PMUX in that's coming directly from the port as input signals. And of course we've got our slave interface. And there is then multiple instantiations of these, one per port. This is the D port, E port, F port, G port, and Z port. So now we've got our EvoXP modified. Now we're going to go into our XP address package, and we're going to add those CSR addresses that we need. So this module is just used to define those addresses. Let's take a look at that. Here we can see after we get past the boilerplate, we are defining addresses as hex numbers. So we've got numbers for port D and E and F and so on. And then those addresses are used at the instantiation to pass those numbers into each of the instantiations so that each instantiation has a different set of addresses. Now, you're going to have to know these numbers then when you're writing software so that when you reference a certain address, you're going to get what you expect back. Now we're going to take a look at our XP info block and see how we can make use of that. This allows us to add additional info registers so that from the sketch you can read information about your custom logic. Inside of the info module, we use indirect addressing to reach our CSR registers. So there's a predefined EvoXP info address that we use for this. And the way this works is that XP info address is used in an indirect fashion. We first write an address to that address, and then we read that address back and we'll get a value. So for each of our values or CSRs that we want to read, these info CSRs, we're going to have a pair of parameters. Here we see EvoXP info num address and num value. So in order to read this num value, what we'll do is first write this number 0, the address 0, to our EvoXP info address register, and then we'll read the EvoXP address register and we'll get this 3 number returned to us. Likewise, if we want to read the type value, we would write the type address, number 3, to the EvoXP info register. Then we would read the EvoXP info register and we'll get this string back, PMUX. Now, these values we're getting back are 32 bits, so you can have any 32-bit integer or hex 32-bit number, or you can have a string of up to 4 characters, because we can only fit 4 characters in 32 bits. So you can't write paragraphs with the data into a single address, but you can have some interesting values in there. You can increase the number of these address value pairs. This first one, by convention, is the number of additional address value pairs that there are. In this case, we've got it set to 3, and you can see we've got 3 additional address value pairs. But you can extend this as far as you want. You could have hundreds of additional registers here by simply adding additional address value pairs with addresses and values. The only other thing you're going to have to change is scroll down a little bit, and you're going to then find this case statement. And this is where we actually make the association between the address and the value. So you would also have to add corresponding address value pairs in this case statement so that you return the right values for the address that you write. So a little hard to wrap your head around initially, but once you get the idea of the indirect addressing, you can see how this is very easy to expand to any length you want. And these addresses that we're using in the indirect addressing don't pollute our rest of our CSR address space at all. We're using a single address. Okay. So now we're at the point where we've done all the modifications to the source file. Now we can just go into our Quartus directory and modify the OpenEvo QSF file. So let's take a quick look at that. The top is all boilerplate. The only line that we modified was this last line, where we are creating a pointer to a new system verilog file called evo PMUX CSR.sv. Note that we're using this OpenEvo_path variable as a pointer to our XB where it lives in the file system, and then to extras design, etc. OpenEvo path is set by our evocommon.qsf settings file, so we can use that here to easily point into anywhere we want into our XB. So now we've got all of our files modified. At this point, we can go into our Quartus directory and double-click on that EvoQPF file, just like we did in the Quickstart. That's going to open up Quartus and then load the project file. Since this is the first time that we are running with this XB, we're going to want to run our OpenEvo update script. And that's going to make sure that our XB is compatible with the Evo BSP that we have. In the future, you don't really need to run this update unless you update the Evo BSP library. Then you'll probably want to run it just to make sure. Once we got that updated, we can go ahead and compile. Now, the first time that you compile after making all these changes, you're probably going to run into some errors, maybe some typos, maybe some syntax errors, maybe the way you connected something in the EvoXP. Quartus is going to complain. You're going to have to go back into your source code, try to address those, rerun the compile, iterate on that process until you get a clean compile. Once we have a clean compile, then we can run our Evo flash load program and load our Evo image into the FPGA. With that image loaded in the FPGA, you will now be able to test your design in hardware and iterate on that process of modifying your source file, recompiling, reloading your FPGA, rinse and repeat. Well, that concludes our workshop. Hope you've enjoyed this rather quick run-through of how the OpenEvo methodology works. Please visit our website at aloriumtech.com to learn more about our products, the Evo and the Accelerate. You can also find a lot of more of our videos on YouTube at Alorium Tech. More workshops, how-tos, videos of fun little projects that people have done with our boards, all kinds of information. And as always, if you have any problems or comments or suggestions, you can reach us at our email address, support@aloriumtech.com. We'll get back to you as soon as we can. Again, I hope you've enjoyed this workshop, and I've enjoyed presenting it to you. Have a lot of fun with your Evo M51 and let us know what you create.